Hello everyone. I hope that you are fine and enjoying good health. Welcome to another lecture of robotics. In today's lecture, we shall continue talking about the path search algorithms. In the previous lecture also, we learned about different types of path search algorithms and why we are doing it. You remember, just to make you refresh the previous things that we have discussed. We wanted our robot to autonomously move from one place to another place, or you can say we want autonomous navigation. And we also learned that in path planning, the path planning is one of the most important capability of a robot that helps the robot to navigate in the environment. So in the previous lecture, we talked about different types of algorithms like breadth-first search algorithms. Then we talked about wavefront algorithm for navigation for the path planning in the grids. And then we talked about Dijkstra's algorithm, and finally the A-star algorithm. But none of these algorithms is perfect. They have their advantages and disadvantages. So one of the disadvantages of the grid search or the graph search algorithms is that they are computationally expensive. What this means? This means that they need a grid or the graph to work to find a shortest path. But what if the dimension of the grid is too big? As the size of the grid increases, the number of cells also increases. Number of cells means number of nodes in the grid or the graph. So as the size of the grid or the dimension of the grid increases, it becomes more difficult to find a shortest path in the grid or the graph. This is one of the problems with the deterministic grid or the graph search algorithms like breadth-first search or wavefront algorithm or the Dijkstra's algorithm or either A-star algorithm. They all fall under the same category, which is the graph search algorithms. So to solve this problem, today we shall study a different set of algorithms that try to solve the problems that were faced by the previous algorithms. So let's start our lecture. Let's have an overview of today's lecture. We shall start with the introduction, a brief introduction of visibility graphs. We shall not go in the detail of this topic because they are not commonly used. They are not very famous. This is one of the methods for path planning, but it's not so popular. So we shall not go in detail. Then we have sampling-based algorithms. So today we shall discuss these types of algorithms in detail because they provide a faster way to find a path. Okay, and they are better than the deterministic or the graph search algorithms in a sense that they find path quickly. Okay, but they have also their own disadvantages. It's not like they are perfect algorithms. They have their own disadvantages. One of their disadvantages is that they are not that optimal. They don't give always the best solution or the best path or the shortest path. we shall see how RRT algorithm, or the rapidly exploring random trees, how they work. They are actually one of the type of sampling based algorithms, and today we shall see how they work, how they find the shortest path. Next we shall talk about RRT star algorithm. RRT star algorithm is one of the variant of RRT algorithm that gives optimal solution, or you can say comparatively optimal solution. And finally, in today's lecture, we shall discuss about probabilistic roadmaps. This is another type of sampling based algorithms, and we shall see how they are different from RRT algorithms and how we can use them to find the shortest path. Okay, let's begin with a brief introduction about visibility graphs. So visibility graph is one of the method to make a graph in your environment or in your configuration space. So let's say this is your configuration space, or let's say this is a map of the environment, and you want your robot to move from one place. So you want your robot to move from this start point here to this is your target point, or the goal point here. So in the previous methods that we have learned, so what we did, we used to either make the cells here using discretization of the space, or we try some kind of graph search algorithms to find the shortest path. But in visibility graph, what we do here, we do exact representation of the C space. It means that we will represent the C space as it is. We will not make any cells or nodes here. We shall not divide our C space into further blocks. We shall use it as it is. Make nodes on the edges or corners of the obstacles. So here we have obstacles. This is obstacle number 1 here. This is obstacle number 2. And this is obstacle number 3. And these are the corners, or you can say edges of the obstacles here. Okay, so the corner or edges where there is a sharp change of the, you can say, direction of your line, then you can say that this is an edge or a corner. So we start with what we do. We make nodes on the edges or corners of the obstacle. So on every corner we make a node here. For example, we look at obstacle boundaries. We have an algorithm that traces the boundaries, and then when we find an obstacle, we put a node here. This is node 1, let's say, and then we see there's a corner. We make a node here, and then a node here and here. And similarly we do for obstacle number 2. And here also we make okay, let's make here also. So now we have make nodes on the corners of edges of the obstacles, and let's see what is the next step. Connect the nodes to other visible nodes using edges. Now what we have to do, we have to just connect the nodes that are visible to other nodes. For example, let's start with our node 1 here. This is node number 1, and we see that from here which nodes are visible to this node. For example, if you're standing here, which other nodes you can see. Okay, of course the first one is you can see is this one here. The second one you can see is this one here. Third one is here. Fourth one is here. Fifth one is here, and this is the sixth one here. The other nodes, for example this one here and here, which are behind the obstacle, they are not visible from this node. If you are standing here, you cannot see the nodes that are behind the obstacle. So yeah, so we repeat this process again. We do it for each and every node. So this is for node number 1. Now we do it for node number 2. For node number 2, it can see node number 1, which is already connected, but it can also see node number 3 here. And node number 3 can be connected to, is visible to node number 4 here, and node number 4 is visible to here, this node, and this node here, and this node is further visible to this node to this node. So in the same fashion, we connect the nodes that are visible to each other. Okay, so let's see what's the next step is. Apply graph search algorithm to find the shortest path. Okay, before this step, we see that after we connected these nodes, now we have a graph. You remember the definition of graph? What was it? Graph was a collection of nodes and edges. So here we have nodes, node number 1, 2, 3, 4, 5, 6. There are many nodes, and then we have edges here. This is, let's say, edge number 1, E1 here, and then this is E2 here. So we have edges also. Edges are the links between two nodes that connect them. So we have a graph here now. We have nodes, we have a connection between them, which are the edges, and now it means that we can use a graph search algorithm to find a shortest path in this graph. So what we do, let's say this is our starting point, and this is our goal point or target point, and we want that our robot moves from here to our goal point. Then we add our start point to the graph, and let's see, it is visible to this one also, and it is visible to this one here also, and also let's say it's visible to this one here also, and here also this one. So we connect our starting point to the nodes, and same we do for the target point. Now we just use any graph search algorithm. For example, we can use Dijkstra's algorithm or A-star algorithm to find the shortest path in this graph. And remember that we are taking our robot as a point here. We're taking our robot as a small point, but if the robot is, let's say you want to represent it like its exact size, then you have to make the obstacle also bigger, which is called inflation of obstacles. If you remember from the previous lectures, we discussed about this thing. So if you want your robot to be bigger in size, then you also have to make the obstacle bigger, okay, in proportion to your robot, and then you can use your robot as a point. So for simplification, we haven't done it, or we considered that the obstacles are already inflated. It means when we say that our robot is a point robot, it means we have already made the obstacles bigger in proportion to your size of robot. Okay, so this method is somehow complex and impractical. And that's why it's not commonly used. Mostly we use either the graph search algorithm, for example, the grid types algorithm, like discretizing your search space into small cells, and then use graph search algorithm to find the shortest path. Or mostly we use also the sampling based algorithms. They are less computationally expensive and they are easier to implement also. But just for your knowledge, we have mentioned this visibility graph, so you should know that what are their other types of path search algorithms. So when you here apply the let's say the Dijkstra's algorithm, so what will happen here, the Dijkstra's algorithm will try to find the shortest path, and it will start moving maybe here, and then here, and then here, and then here, and then finally reach the target. So this is another method for path planning. Now let's move toward our next method for path planning, which is sampling based algorithms. Again, we have seen some disadvantages of the visibility graphs, and we have also seen some disadvantages of the grid search algorithms or the graph search algorithms, like Dijkstra's algorithm, A-star algorithm, and breadth first search algorithm. All of them were computationally expensive for higher dimensional grids. So now we present sampling based algorithms that solve this problem. So again here, let me show you for a grid based algorithms, we have, for example, as long as the dimension of your grid is small, okay, then the grid based methods, for example, the breadth first search algorithm, Dijkstra's algorithm, or A-star algorithm, they work like very good, very efficiently. But as soon as the dimension of the grid increases, the number of cells also increases. So it increases actually exponentially. If there are more dimensions, the number of cells will increase exponentially, which makes total number of cells in the grid much higher, so it will take longer time to find a path in a bigger grid. Okay, that was one of the disadvantages I have discussed here. Yes, so we have already discussed this point, that number of grid cells, when the dimension of the search space increases, then grid cells increase exponentially. It means there is no linear combination. If you're here, for example, look at here, if let's say there is a 2 by 2 grid, then how many cells there will be in a 2 row and 2 column grid? There will be four cells, okay? And let's increase now the grid size to let's say 3, and in 3 by 3 you will have how many cells? You will have 9 cells total. And if you make the grid in 3-dimensional, then there will be even more cells. If you take a 3 by 3 3-dimensional 2 by 2 grid, okay, 2 by 2 by 2 grid, then there will be 8 cells inside the grid. So you see that how the number of cells exponentially increase with increasing the dimension of your search space. Now, sampling-based algorithms search for collision-free path from start position to target position. So this is again another search algorithms that searches path from start position to your goal position, avoiding the obstacles in the path or in the environment. And their beauty is that they do this thing in a quick way, better than the previous methods. And we shall see how they do that in upcoming slides. So sampling can be deterministic or random, but mostly we use random sampling for these types of algorithms. But it can be also deterministic, so there is no strict rules here. So now what is sampling? Sampling means just to take a point from your configuration space or your state space or your workspace. You just take a point either randomly or deterministically from your search space, and this process is called sampling. We shall see in detail with the example soon. So the next point says that quick solution finding for high dimensional spaces. So this is one of the advantages of sampling based algorithm, that they find solution quickly, relatively quickly. So if you compare the grid search algorithms, for example the Dijkstra's algorithm, you give the sampling based algorithms and the grid based algorithm same kind of map of the environment, and then you start your algorithm, you will see that this sampling based algorithm, they find path quickly as compared to Dijkstra's algorithm. And especially this difference is very noticeable when the grids are much bigger or they have a higher dimensions. So you can see this difference very well. So sampling, what is exactly does is it approximates your free space. So in your environment you remember we have some obstacle space and then we have free space here. So let's say this is our obstacle here, and this is our free space. So what sampling does, it approximates your free space. It says approximately where your which points or which samples are the free space. Okay, because we need a model of in the environment, we need a model of the free space available in the environment. So sampling does, it takes samples and it tells you where either this is a free space sample or not, and either the free space exists here or not, and how the free space looks like. Okay, and the advantage of is that less samples are required to represent the free space, especially in sampling based algorithms. You need less points to represent the free space. But if you see your deterministic, the grid method, you have to use a lot of cells to represent your free space. Okay, and if you don't use a lot of cells, the resolution of the grid is not so high, then there is a chance that your algorithm will not able to find a path. It will fail to find a path, or it will give you a very say not optimal path. Okay, this is another concept like probabilistic complete and the resolution complete. We have already discussed it in the previous slide, and let's see one more time. Probabilistic complete means that actually we have discussed this one here, resolution complete, I guess, but not probabilistic complete. So probabilistic complete means that if there are enough samples available, okay, or if the samples approach infinity, then there are more chances that your algorithm will find the solution. On the other hand, resolution complete means if the resolution of the grid is small enough, okay, then there is a guarantee that your path planning algorithm will find the shortest path or the solution. So probabilistic complete, it depends upon more samples to find the solution, and resolution complete requires a fine grid, okay, more number of cells to find the shortest path. So one of the type of the sampling based algorithms is called rapidly exploring random trees. So this is a sampling based algorithm which uses trees, not like a like natural tree, but it's a graph tree. And I hope that you can remind that we have studied a lot about trees and graphs. So this algorithm uses a tree to search a graph. To search a path in your configuration space. The second type of sampling based algorithms is the probabilistic roadmaps. So these types of methods, they use graph to represent your free space. So they are different in the terms that the first one it uses tree, and the second one uses graph to represent your free space in the environment or in the configuration space. So in a general, how sampling based algorithm works. The first thing is choose a sample from your C space or state space. So let's say this is our configuration space, and this is, we have obstacle here. So the first step says that choose a sample. The sample can be random or already it can be deterministic. So let's choose a sample randomly. We choose a point here. So this is our sample S1. Evaluation function. So every sampling based algorithms, they have some kind of evaluation function. So what this evaluation function does, that they determine the nearest free space samples. So this is the task of your evaluation function, which is a part of every sampling based algorithms. So what they do, they look for the nearest free space samples that are available. So this was the first sample, so it has no other nearest samples available. But if we take, let's say, one other sample here, one more random sample S2, then it has now available the nearest sample S1. Okay, so we need some kind of evaluation function to determine which one is the nearest sample. Let's say there is one more sample S3 also. So now what the evaluation function does, it determines which one is the closest point, either S1 or S3, which one is closest to S2, either S1 or S3. So this is a function of your evaluation function. A local planner that connects with the new sample. Okay, so once you have determined which point is closer, okay, so of course from S2 the closest point is S1. So now you have to connect them using a line, or maybe some kind of curve. Maybe it depends upon the constraints you have. Let's say if we have an obstacle here, then how you gonna do that? How you gonna connect these 2 points? So this is a task of the local planner, that how to connect these 2 points either using a straight line or using some kind of other curves. Build a graph or a tree. So in process of this, making samples and then using evaluation and then connecting these samples with local planner, what we are doing is we are making a graph or either a tree. For example, if we connect them, S2 is connected with S1 and S3 is connected with S2. So it looks like a tree. If you see here, this is S2, and here this was our first sample here. S1 and S3. So if you look here, that the S2 is connected with S1 and S3 here. So it means that it looks like S1 has only one parent, which is S2, and S3 has only one parent, which is S2. So this can be considered as a tree. Okay, but if they have like multiple parents, for example, let's say there is one sample S4 here. Let's say one more sample. Where is S4? Okay, here is S4, and S3 is connected with S4. So if, let's say, S4 is here and it has a child S3, so then it means that now S3 has 2 parents, S2 and S4. Then now this is not a tree, this will be a graph. So in a tree, each node can only have one parent, but in the graph each node can have multiple parents also. So this is the basic functioning of the sampling based algorithms. Just take a sample from the search space, then use some kind of evaluation function to find the nearest node or the nearest sample, and then use some kind of local planner to to connect your new sample with your previous sample. And in this process of connecting the nodes or two samples, you are making a graph or either a tree. Okay, so one of the type of the sampling based algorithms is the rapidly exploring random trees or RRT. So rapidly exploring random trees, this is a type of path planning or path search algorithms that searches for collision-free path from initial state to goal state. So this is like the main goal is to find a shortest path. So why it's called a random tree? Because it makes a tree during connection of the nodes, connection of the samples. It makes tree. So let me change the color here. So this is your start point, this is your target point here, and what it does, the main goal is to find the path avoiding the obstacles that reaches to your target location. And since it's a sampling based algorithm, so it uses samples, sample for example S1, then S2, then S3, S4. So all these samples and here let's say S5. So each time it samples, okay, and then it checks that whether this sample is in the free space or not, and then it uses some kind of what was the name of this thing? Evaluation function. Yeah, it uses evaluation function to find the nearest sample. So it uses evaluation to say, okay, from let's say from S1, or let's say this was S0, we call it, because the graph always starts from S0. So from S0 it says that, okay, which one is the nearest one, either S2, S4, and in this process it makes a tree and reaches the target point. A single query. So this is one of the you can say disadvantage of RRT algorithm, that it only offers single query. Single query means you can only one time, each operation you can only use one time planning. So you cannot use it, for example, once it planned a path, you cannot use it for finding multiple targets. Okay, let's say if in the first operation it says that this is the shortest path, and then once the path is complete, the algorithm stops. So let's say next time I say that, okay, I wanted to actually go to target 2, T2 here. So now you have to again do sampling, all these sampling points, then you have to use evaluation function, then you have to use local planner, and then maybe you can reach your new target. Okay, so for each time, for each new target, you have to repeat the whole process again. So that is why this algorithm is single query. But there are multiple query algorithms, and you shall see that later. The probabilistic roadmaps, they can be used for multiple query, because they make a graph, and in this graph you can use multiple times goal finding. Okay, so this is again one of the advantage of, because it's here says as rapidly exploring. So it rapidly it explores your free space in your configuration space rapidly. Okay, it acts like a tree that grows from your start point to your whole configuration space. It fills the tree very quickly in all directions in your configuration space, and that's why it's called rapidly exploring random trees. So it has one of its component is the sampler. What the sampler does, the sampler randomly samples your environment according to your the normal distribution. It randomly samples your environment, and within the bounds of the configuration space. For example, the maximum value from this is 0, 0 here, and on the y-axis you have, let's say, maximum value of 10, and on the x-axis this is, let's say, also 10 here. So sampling point should be within the range of maximum x and maximum y. The sampling point should be within this range, and whenever you say I have a sampling point here, it means x-axis, let's say x-axis 1, and on y-axis it's 9. This is your random sample S. So each rapidly exploring random trees, it must have a sampler that samples your configuration space either randomly, or in some cases it can also be deterministic. So what deterministic means? That deterministic means you already know the location of your sample. Okay, you have already planned it where I will sample. For example, I know that if the goal is here and this is a straight line between goal and target, so I will sample. Okay, let me change the color. Let's make it black. So one method of deterministic sampling is I will sample here, like in a straight line toward goal, or within a specific range of this. So this is an example of deterministic sampling. So I know that where the goal is, which direction the goal is, and I only sample in direction to the goal or near to the goal. So this is one example of deterministic sampling. But if you say a random sampling, random means it can have a point here also, it can have a point here also, anywhere, even on the other side of the target also. Okay, so the next thing is the nearest node. So once you have a sample of your configuration space, as we already discussed in the evaluation function, we now need to find the nearest node. Okay, this is the task of the evaluation function, because there are thousands or even more nodes, and now you have to select which one is the nearest node. So how you can do that? You can just measure the distance. For example, if this is your current point, okay, or the sample point, and you need to find which one is the nearest node here, then you can just measure the distance, Euclidean distance, and see which node gives you the shortest distance here, and the one with the shortest distance, this will be your nearest node. Let's say this one has the shortest distance, then this will be your nearest node. And then we have local planner. I think we already discussed it already. So the task of the local planner is to connect your sample point with your nearest node or to your tree. So it can be either a straight line, or it can be also some variation depending upon the robot kinematics, which we haven't studied yet, and when we study them, then we shall also discuss them in detail. So let's see some steps of RRT algorithm, how it works. It says that initialize the tree with start node. This is our goal point T, and this is our start point S. And let's say we have a tree, and in this tree we add this in a tree. The first node is our start node. Okay, this is our root node. Start node is root node. So you remember that in each tree there is a root node where the whole tree starts, which is a parent of the root node has no parent, you can say. Okay, so this is the first step of the RRT algorithm. The next step is define max sample size. So here you have to see how big is your configuration space or your state space. For example, this is, let's say this is 4 here, or let's say 5 meters in y-axis and 5 meters along x-axis. This is your x-axis and this is your y-axis. And next is sample a point in state space. So this is, if you take it as a state space with a size of 5 by 5, 5 along x-axis, 5 along y-axis. So now you have to take a sample randomly. So I prefer random sample because the name of these algorithm is rapidly exploring random trees. So that's why it makes sense if you make random sampling. So let's take a sample randomly. Okay. For example, I take the sample here. Let's take it here. And this sample have coordinates. Let's call this sample S1. And it has a coordinates about x-axis about maybe 2.5 and y-axis also 2.5 or 2. So this is our sample 1. And the next step of what the algorithm says that find the nearest node to the sample point. So now within there can be also within a specific radius here. You have to find a sample point here. Okay, so in this case, let's say S is our nearest only one. So what we do, we have found that the nearest node is S, because there is only one node. So we say that okay, the nearest one is S. Use local motion planner to connect the nearest node with the new node. Okay, I missed one step here. Let me add it here. So here you can see we have use local motion planner. Before this step, use local motion planner to connect the nearest node with the new node. So there is no new node yet. You have to first make the new node. So make a new node at a distance threshold d from the nearest node. So this step we missed it. Okay, so once again, we have initialized the tree with the start node. We say our tree has a start node, and what we did again, then we define the maximum sample size, and then we sample a point S1 in the state space. Then we find the nearest node to the sample point. So this is our sample point, and the nearest node to this is S. And there is also one node T, but you can say that either it's not nearest, or you can say it's or it's not within the specific radius of this our where we search for the nearest node. Okay, and then we have make a new node at a distance threshold d from the nearest node. So now here we have to make a new node. So S is the nearest node, and this is sampled node. So what we have to do, we have to, in direction of the S1, we have to make a new node at distance d. This is new node, we call it, okay, N1. Okay, so the distance is always d. This is a threshold where we allowed to go there. Okay, so that's how we make a new node here, and then we use local motion planner to connect the nearest node with the new node, and we have already done it. We use a straight line to connect these two, the nearest node and the new node. We use a straight red color line, or you can say the edge. Okay, and after that, if the motion is collision free, then add the new point to the tree by making an edge with nearest node. This is again a little bit repetition. You have to basically see that this point, this new node N1, it should not be in obstacle space. Okay, it should not be somewhere here or here or here. It's not allowed. If it's inside the obstacle space, then this is rejected. You cannot add it into that tree. Okay, and also you have to make sure that the edge that connects the nearest node with the new node, should I mention it here, or I think it will become more like messy. So remember that this is the sampled node, this is the nearest node to the sample, and this is a new node that we have made at a distance d from the nearest node. And now we check it whether this node is in a free space or not. Okay, if this node and the edge that connects the new node with the nearest node, if they are both in the free space, okay, then what we do, we add this node to the tree. Here was our tree, and we say that okay, node N1 is a child node of node S. Okay, and What next? If a new point is the goal point, then the algorithm stops. Okay, this comes later, but there's a repetition here from step 7. What we do, we go to step again from here, we go to step number 3 here. We go from step 7 to step 3 again, and we again sample a point here, and let's say the second sample point is again the second sample point is here, let's say S2 here. Okay, so now we have to find which one is the nearest point in the graph, in the tree we have, which is closest to this sample 2. Okay, that's what the next step says, find the nearest node. So from our sampled point or sample node S2, which is the nearest node in the tree, we have to look for it. There are now 2 nodes in the tree. Here you can see one node is S, one node is N1. So S or N1. Now what we do, we measure the distances from our sample node to node N1 and to node S. So of course, which one has the minimum distance, we select this as the nearest node N1. Now what we do, we measure the we make a node N2 at a distance d in the direction of S2. We make a node N2 so this is node N2, and so this node is at a distance d and it's also in direction of S2. Okay, and now we have to look for whether this is in collision with the obstacle or not. Of course, this is in the free space we have. So now what we do, we try to use local planner to connect it with the new node. This was the nearest node, and this is our new node. Okay, and we connected it, and we see that we see that the edge that connects N1 and N2, this is also not colliding with the obstacle. So now we add N2 in the tree, and the parent of N2 is N1. Here we added another node in the tree, which is N2. Let's take another sample, and so I think the concept is understood. I hope so. So we keep this process doing. Then there will be a node at a distance d, which is N3, and then there will be a node at distance d, which is the N4, and then we keep this process till we reach our N5, N6. We keep repeating this process till we reach our target node. Okay, and so this is how the RLT works. And for simplification, I have only drawn the nodes that are closest to the target, but in reality there will be a tree, and tree, like, it's really a graph. That, for example, a point can also be in the sample point can also be in this direction. Then you have to grow your node here also, or then here also, like this. So because it's random sampling now, so it will sample in each and every direction. So sampling points and your nodes can be in any direction, and the thing is you have to repeat the basic steps. You have to sample, you have to find the nearest node, and then you have to make a new node at a distance d, and then connect this node to your nearest node or in your tree. So that's how you make a tree here. And once you reach your target point, okay, then the algorithm actually stops searching, stops sampling new nodes. And now the only thing is how you find the path. You have to just follow from the goal node, you have to keep following the parent node, okay, till you reach your start point. So this will be your shortest path. Actually, this algorithm is more better if you implement it, then it's more easy to understand, because making random nodes, it's a little bit tricky here, but I hope that it will be more clear once we implement this in MATLAB. So yeah, so the tree will be like, for example, let's try to make the tree here. Okay, there is one node here, then there is one node here, and let's say here we reached our target node or goal node here, and these are the other nodes. Okay, so now we are at target node and we want to reach our starting node. What we need to do in the tree, we look for what is the parent of this node. Of course, this one is parent. So we go to this node, and then here we look what is the parent of this node. This one is the parent. We go to this node, and similarly from here we go to our start node. So from here, this will be our path to our goal node or target node. So this is how rapidly exploring random trees work. And this was a little bit simplified, very simplified example. And if you see, when you see in the reality, this trees grows in every direction. It fills out because it's randomly sampling, and that's why it fills out all the space in your configuration space. So the only thing is that in each node there can be only one parent. There cannot be two parents of the same node. Okay. So this is how this algorithm works, and let's move to the next slide. Okay, so now we have RRT star algorithm. One of the problem was with RRT algorithm is that it doesn't give you the shortest path always. This path will not be optimal, and the reason is that because the samples are random. You can see the path is like zigzag. It's not straight. A straight path should be like straight line, but the path is like zigzag, and this is because this is random sampling and the random addition of your new nodes to your previous tree. So that's why this algorithm doesn't give the shortest path. Okay, but its advantage is that it is fast. You see that it has found the path with very few number of nodes. But if you have to do the same thing with the grade search method, you have to use a lot of cells, maybe 5 by 5, 25. You have to use 25 nodes here. Okay, if each grid cell is 1 meter, then you have to use at least 25 nodes here. But here you see that only like 10 to 15 nodes this algorithm has find the solution. And also you see that a few nodes are required to represent your free space. So that's why this algorithm is fast as compared to grid search methods or graph search method, but the disadvantage is that this is not optimal. Okay, it will not give you the shortest path. It will only give you like a feasible path. Now what is a feasible path? Feasible path is like it reaches goal and avoiding obstacles. This is the minimum requirement, but it is not a shortest path. To solve this problem, someone proposed RRT star algorithm, and it is similar to RRT algorithm, but it uses rewiring of graph. So how it works is that it starts with the same thing. So there is an starting node, and then you sample a node, let's say a node S1, and then there is a node let's say S3. So then you, at a distance d, you connect your new node. So the nearest one to S1 is, let's say, S. So at a distance d, you connect your new node here, which is N1, and then there is a sample S3. Sorry, it should be S2 actually. So the nearest node to the sample 2 is N1. Okay, we see S1 and N1. So the nearest one here is N1. So you make a new node in direction of S2 at a distance d. This is N2. So what's the difference here? If you remember from the RRT algorithm, we keep repeating this process always. Okay, we keep adding new nodes to our tree which are nearest to the nearest node. We keep adding, and which are collision free. They are not in the obstacle. Okay, and we keep repeating this process till we reach our target point. But what's new in the RRT star, that once it add the new node to your tree, for example, we have added N2 to your tree which has already S and N1. So what it does, within a specific radius, so from here, from N2, it looks for within a specific radius, let's say R, it looks for the nodes where it can have further shortest distance. It can minimize the distance. So again, it looks from here, it looks at, okay, it has found a node S, and now it knows that it has found that going from N2 to S is shorter than going N2 to N1 and then N1 to S. Okay, so this is called this is a difference in the RRT and RRT star algorithm, because in RRT star algorithm you look for always some shortest path, and also you change also the parents of the node. So previously N1 in the tree, in this tree, it was like S was connected to N1, and N1 was connected to, let's say, N2. So now so the parent of N2 was N1 and the parent of N1 was S. But in RRT star, since we do this shortest distance thing or rewiring thing, we rewire our tree again. So we have found that the shortest distance between N2 and S is the straight line, not going through the N1. Okay, so what we now do, we make the parent S we made the parent of node N2 directly S, not N1. Okay, so now we have node N1 and N2, and both have parents S. But previously, if you use the RRT algorithm, N2 has a parent N1, N1 has a parent S. But in RRT star algorithm, we rewired our graph. Okay, we said, okay, if we found a better, shorter solution, so we should change the parents. So this is called rewiring. And so this is how we get the shortest path. And if we do it for all the nodes, okay, then it will give us the shortest path from start to target position, and this path is much better than the RRT algorithm. So we keep repeating this process. For example, let's say our next node is S3, and in S3 direction we have where we make this now. Let's make in this direction. Again, in this direction we have no, not in this direction. Okay, let's say the other sample is S3 and it is here. This is S3. Okay. Now, from what RRT algorithm says, in direction of S3, you have to look which is the shortest, which is the nearest node in the tree, and from here N2 is, let's say N2 is the nearest one. So we make a new node in direction of S3 at a distance d, which is N3. Okay. Now, so what's the parent of N3? It is N2, and N2 has a parent S. Now again, what we do, if this is RRT star algorithm, then we do rewiring. And how we do rewiring? Like we did for N2. We from N3 we look at a specific radius R, all the nodes here. Okay, we look all the nodes in the tree, and we look for, okay, going from N3 to S, which is the shortest one. So we found that, okay, N3 to S directly going, it is shorter than going N3 to N2 and then N2 to S. So what we do, we remove this edge. We say, okay, N2 is not the parent of N3. Instead, N3 has a direct parent of S. N3 has a parent S, and we make an edge. We connect the N3 with S, which is the shortest path. So this is the main difference between the RRT and RRT star algorithm, because there is this thing called rewiring, which we do to make shortest path, and this is a reason that RRT star gives the shortest path. We keep this process same like in RRT till we have found the goal or the target node. Okay. So this RRT star algorithm, this is probabilistically probabilistically complete, and the reason is that it depends upon samples. It means that if the samples are approach infinity, if there are infinite samples, then this algorithm will find a path. Okay, so it means we need higher number of samples to find a path if it exists, or to make sure that the algorithm finds a path. Then we asymptotically optimal. This is another speciality of this algorithm. This means that this algorithm will find the shortest path. Okay, if you have if the number of samples increases, if you have more number of samples, then there are chances that the solution will be the optimal shortest. So to find an optimal solution, you need like infinite samples. Okay, let's now move toward the probabilistic roadmaps. So we have learned that sampling based algorithms had two types. One was the rapidly exploring random trees, and the second was the probabilistic roadmaps. The difference between probabilistic roadmaps and the sampling trees was the probabilistic roadmaps, it uses a graph to represent your configuration space. But the rapidly exploring random trees, they require a tree to represent your configuration space. So this PRM, in short we call them PRM algorithms. They use sampling to build a roadmap representation of the free space. So what they do, they use same like sampling like we did in RRT. They use sometimes random sampling, and sometimes they also use deterministic sampling. And they use sampling to show that where is the free space located. So now what is a roadmap? Roadmap is an undirected graph. Means robot can move in any direction along the edge. So undirected graph has no arrows, no directions on it. It means that the motion is possible from one node to another node, and also from second node to back the first one. So this is how, let me show you. This is how it samples sample the configuration space randomly, and then it connects these sample points to make a roadmap that looks like this. So this is, you can see that this is a graph with nodes and edges, and we call it a roadmap. And this method is efficient as compared to grid. As we already have discussed, this is a sampling based algorithm, and we require less points, less nodes to represent our free space. But if you have used here a grid method, you have to use a lot of nodes, cells, to represent your free space in this configuration space. But using sampling based algorithms, we use less nodes, and we can still find path. So that's why it is efficient. And in what thing it is efficient? It is efficient in finding the shortest path. If you use sampling based algorithms, especially the probabilistic roadmaps, then it means that our algorithm will find the path in less time, and also it will require less space or memory in computer. This is multi-query method for path planning. Okay, what multi-query means that you can use it multiple times to find a path, and the reason is that it makes a roadmap or an undirected graph, and you can use this graph multiple times. You can use it, for example, if your start point is here and first your target was here, you can say, okay, you can use any graph search algorithm, for example, Dijkstra's algorithm or breadth search algorithm or A-star algorithm. You can use on this graph to find the shortest path to your target. Okay, and let's say after some time you say, okay, this was not the actual target. Actually, I wanted to go here. This is my target too. So now this time you don't have to again do sampling and all those things. Just this graph is already there. You again on this graph, you use any graph search algorithm, for example, Dijkstra's algorithm. You give this as a source, this is your new target, and then Dijkstra's algorithm will give you the shortest path from your start to your target position. So this is the multi-query, you can say, advantage of this types of method. But RRT algorithm, they are not multi-query. We have already discussed. Every time you have a new target, you have to again do the sampling, again all those stuff about the evaluation function, and you have to make a new graph, a new tree, and then you reach your new target. Okay. So I hope that you have realized that till here, that each of these path search algorithms, they have their advantages and disadvantages. Okay. So none of them is perfect. Everyone have some advantages and disadvantages. For example, the RRT is fast, but it's not multi-query, and this PRM it's multi-query, but it requires an additional path search algorithm, okay, to search a path, for example, Dijkstra's algorithm. So everyone have their own plus and minus points. So now we see that how step by step how this PRM method it builds a roadmap or a graph. So the first thing is randomly sample the C space. So this is our state space, C space. Just randomly take a sample here. Let's say I take in the middle point or somewhere here, let's say. Sample point should not be in the obstacle. So this you have to make sure. Let's say if your sample point is inside the obstacle, then it is not considered as a sample point. Okay, you are only allowed to take samples that are in the free space, and this is true also for RRT algorithm also. I think there I forgot to mention, if your sample point is inside the obstacle, then it is not considered as a sample point. Check the neighboring points within the threshold distance. So this is because this is our first sample point. It doesn't have any neighboring one, so we can't do anything here. The fourth step is connect the sample point with the nearest neighbor point. So yeah, so there should be some kind of connection here, but since this is the first one, so we can't do anything. Check if the edge is not in collision with the obstacle. So again, repeat the above process to make the roadmap. So from here we repeat that. Let's take a second sample also. So let's say the second sample is here, S2, and from here we now can apply these things. So check the nearest point within the threshold. Okay, and let's say this is the nearest, S2 is the nearest point, which is the only point. Connect the sample point with the nearest neighbor point. Now we use an edge or a straight line to connect these 2 points. Check if the edge is in collision, not in collision with the obstacle. Yes, so there is no obstacle within these 2 points, or there is no edge, the edge is not colliding with the obstacle. So we add this point S2 in our graph or in the roadmap. We repeat it again. Let's take another point. This is, let's say, S3. Now we see that, okay, S3, the nearest point to S3 is S1. We try to connect it here like this, but since this is the this edge is collision with the obstacle, so we cannot add it. Okay, so we just remove it from here. Let's take another sample. This time we take it S4. So S4, we say that, okay, which one is the nearest point to S4, and this is, we have S3. We connect it, and then there is no collision here, and then we say that, okay, we have connected to the nearest point. We take another sample here. S5 here, and we look for the nearest point. Nearest point is S3, and S3, if we make an edge here, then this will be in collision with the obstacle, so we don't add it. We let it like this. And let's take another sample, that is S6. Okay, S6, the closest point is S1, and we add this point to S1. And so similarly we make more samples. Let's say here one more sample, S7, and we add it to S7. So similarly we make more samples, S8, and we try to connect them. S9, we try to connect them with the nearest points until we get a good connection between the between all the points here. S10. So we get a good graph here. So what we do here now, once we get this roadmap or a graph here, okay. So what we do now, first change let's say this was our start point here, and this is the target point, and now we want the robot to move from this point to this point without colliding the obstacles, and it has also to find the target point. The first thing we do, that we check which is the nearest node in this roadmap or in this undirected graph. So the nearest one is S2. We add the node S to our roadmap by joining it with the S2. Okay, and to the target, the closest node is S3, so we join it with target. And then now we have a graph, and in this graph we can now use any graph search algorithm, for example breadth-first search, Dijkstra's algorithm, or A-star algorithm, to find shortest path in this graph which lead us to the target. Okay, so this is how the PRM method works for path planning. So let's summarize today's lecture. So today we learned about different, like more methods for path planning and path search in your state space, in your environment. And we discussed about visibility graphs, and we said that, okay, they are not used often, although we should know that this is also one method for path search. And one of their specialties is that they require exact representation of your configuration space. They don't require that making cells or further nodes or something. But they are difficult to implement. That's why we don't use them often. So mostly we use either the grid-based methods or the random sampling-based methods. Then we talked about RRT algorithms, which is the first type of the sampling-based algorithms. We learned today, okay, how what is advantage of these RRT algorithms. They are fast, they are quick, but the disadvantage was, especially for the RRT, was the path was not shortest. Okay, there were a lot of zigzags, or so the path was, like, you can say that it was a feasible path. It avoided the obstacles, but it was not the optimal path. Then we talked about the RRT star algorithm, which was an improvement in RRT algorithm. And here we said that, okay, we use a technique called rewiring, in which the nodes, it was similar to RRT algorithm, but the difference was whenever we select a new node, we also see the neighboring nodes, and if we found a better or the shortest path, then we change the parent of this new node to that shortest node, okay, the nearest one, the closest one. So this rewiring process in the tree, it gives us shortest path from start to target position, and that's why RRT star is optimal, probabilistically optimal version of RRT algorithm. Then we see when we saw that these RRT types algorithm, they are single query, they are not multi-query. So to solve this problem, we introduced a probabilistic roadmaps method, in which we make a roadmap or an undirected graph in your configuration space. This probabilistic roadmap method is also a sampling based method. It means it will sample randomly or either deterministically sample from your configuration space, and then it connects these points with each other to make a roadmap or an undirected graph, and then we can use any graph search algorithms to find the shortest path. And the advantage of this types of algorithm is that it was multi-query. It means once the graph is there, you can use this graph for multiple path planning tasks. So we shall end our lecture here, and thank you very much for your attention.